Now that we've looked at power functions, we're going to look at polynomial functions. Let's turn to a little introductory problem. So imagine you've got an oil slick, and suppose it's a disk and it has some radius. We'll assume that initially the oil slick has a radius of 24 kilometers. Okay, so this is an oil slick that's been spilled by a tanker in the ocean, but it's going to increase as time goes by. It increases by 8 kilometers per week. Okay, so of course we've got that the area of that oil slick is a power function. Okay, we've seen that before. But now R is also a function of the number of weeks that go by, and that's just described by a linear function because, right, if you've got the number of weeks, W, and R, you initially start with 24, and then you've got a constant increase, so constant slope. If you go forward by 1 week, it goes up by 8. Okay, each time we'll go forward by 1, go up by 8 all the time. So you're going to end up with a linear function. Okay, and its equation is 24 because that's the y-intercept plus the slope, which is 8 times the variables. Okay. So from this, we can combine both functions together, compose them. We could find the area as a function of number of weeks that actually go by, and that would correspond to pi times 24 plus 8w squared. Okay, and if I expand all this, I'm going to get the following polynomial. Like that. Well, there's no w square here. Okay, just like that. 384. Okay, okay, and that's hard to read. This is a plus sign. So what do we get here? Are the sum basically of 3 power functions. You've got this one, that's a constant function, the power is 0 here. Here this is a linear function, but it's a power function, and you've got this power function where the power is 2. In each case, you've got these. This is the coefficient. You're here the expression itself and the coefficient are one and the same. This is the coefficient, and this is the coefficient. Okay, but we've got overall 3 power functions, and the power is a non-negative integer. Okay, so that's what a polynomial is. It's going to be a sum of power functions with non-negative integer powers. And let's write that down. Okay. So the notation for our polynomial, we've seen this before. So this is just looking again at old objects with the point of view of functions. Okay. Through the lens of functions, we've got an, that's going to be our leading coefficient, times x to the n. Okay. Plus some other stuff, but maybe immediately I'm going to write down, this is going to be the leading coefficient. Okay. N is going to be the degree. I'm going to add this as well. So actually after that, the next coefficient is an minus 1. So for example, if this one was a7 x to the 7, the next one is 1 less. So this is why I'm writing an minus 1. So it would be a6 x to the 6, you see. Okay, so x n to the n minus 1, and you just keep on going like this. You've got a2 x2 a1 x to the 1, and finally a to the 0 x to the 0 x to the 0 is just 1. So that's our so maybe if you want like an example with numbers, okay, so example here, f of x equals I could have like 7x to the 6 plus 3x cubed minus 7x squared plus x minus 5. Okay, so the largest power of n, okay, that's called the degree of the polynomial. So here the degree of this polynomial here is 6. Okay, the entire term here, okay, with the largest power, that's called the leading term. Okay, so our leading term here would be all this. 7 would be the leading coefficient, 6 is the degree. There's also this guy that's important, that's the constant term. Or okay, so the constant term here would be minus 5. Okay, and that's pretty much it. Okay, now these functions, right, you can replace x here by any value that you like, right? You can always raise a number to any power that you want, especially if it's a positive, non-negative power. If it's negative, you have to watch out because you can't divide by 0. But here, all the powers are non-negative, so the domain here is always R. Okay, so what that means is that you cannot have functions like that are polynomial functions that have graphs that have asymptotes in them, for example. Okay, you cannot have something that would look like this. Okay, that's not possible. There would be like a some sort of horizontal vertical asymptote, so this is not possible. Okay, and we'll see also later on that you cannot have horizontal asymptotes. Okay, no vertical asymptotes. So that's because it has to be defined everywhere. So you cannot have a place where the graph is undefined, or you cannot have a graph that's like this. That's a graph of a polynomial function. Okay, because there's a hole in it, and the domain should be always all real values. And I'm going to add here also no horizontal asymptotes, but that's not explained by the fact that the domain is real, all real numbers. It's explained by some other property. Okay, but just know that you cannot have any sorts of asymptotes when you've got a polynomial function. And I'm going to explain now why you can't have horizontal asymptotes. And for this, we're going to look at the AND behavior. Okay, so an horizontal asymptote is when a function reaches, becomes flat in the end. Okay, and that happens, for example, let's say this is y equals 4. You'd have like a function that would get really, really close to 4, for example, so we become flat. Okay, so that would be a function with an horizontal asymptote. Okay, so y equals 4 is a horizontal asymptote. Okay, and I'll explain why you can't have this for polynomial functions. So here, let's look at the long-term behavior, okay, near the asymptote. So if we look at here, okay, what happens is that if x becomes large and positive, then f of x, the function values, right, if you look at the y values on the curve, okay, they're going to get close and closer and closer to 4. Okay, and then we're going to show you that you cannot have f of x becoming closer and closer to a constant if you've got a polynomial function. You can have this if you've got a power function. For example, if you've got x to the minus 1, okay, it has actually both vertical and horizontal asymptotes, but you can see here Looking at this, we've got horizontal asymptotes. But you've got a negative power here, and this is what makes the difference. In our case, we cannot have negative powers when we're dealing with a polynomial function. So that's why we won't be able to have some sort of behavior like this. And there's also here vertical asymptotes, which means we're getting closer. We get closer and closer to infinity as we get closer and closer to a specific x value. Here, x equals 0, and that's due to the fact that this is 1 over x, and when x is close to 0, we're dividing by a number that's close to 0, and therefore 1 over something close to 0 will be extremely large. So therefore creating these vertical asymptotes. So don't worry if that's too much. We're going to return to those vertical asymptotes later on in the chapter. So let's just erase this for now. Okay. So let's move on to and behaviors of polynomials. And we're going to look at an example, and you're going to see immediately how we can analyze the long-term behavior. So here's a polynomial. Okay. And I want to show you something. I'm going to do something you've never seen before, I think. I'm going to factor, okay, only the first term, okay? And actually, I'm factoring not any term, I'm factoring the leading term, okay? So what I'm going to do is I'm going to multiply and divide by it, okay? So I'm going to multiply by this. And at the same time, I'm going to divide by it. Okay, so I haven't changed anything. But what happens is that now the leading term is in front of my bracket, and I will now simplify this bracket. So this bracket here, dividing by a single term, means that every term above is divided by that one. So this is the same as 3x cubed over minus 3x cubed over minus 3x cubed plus 2x squared over minus 3x cubed plus 1 over minus 3x cubed. Okay, and let's simplify this. Okay, so this is just 1. This guy simplifies to, well, there's 2 over minus 3, that's minus 2/3. And x squared over x cubed, I'm going to keep positive powers, by the way. So I'm going to write it as 1 over x, right? X squared over x cubed is 1 over x. And then here, minus 1/3, 1 over x cubed. Okay? And this is what I want to show you next. Look at these guys. Okay? I'm going to end up by factoring the largest, the leading term, right? The minus 3x cubed. After simplifying inside my bracket, I'm going to end up essentially either with a constant, so I've got a constant here, or negative powers of x. So in other words, 1 over a positive power of x. Okay, and if x is large for any of these two, for example, okay, imagine x is large, like let's say 100,000. Okay, that's going to become super small, right? That's going to be like really close, very small. Okay. Same goes for 1 over x cubed. If I take 100,000 and cube it, okay, that's actually super large. This is 10,000. 100,000 is 10 to the 5, so I'm going to get 1 over 10 to the 15. So that's really small. Okay, so very small values. Okay, as x tends towards either infinity or plus or minus infinity. Doesn't matter. Okay. So in the long run, okay, these terms here, okay, they play no role in the behavior of my function because they become almost 0. Okay, so if I look at what remains is, it means that this is approximately equal to minus 3x cubed, almost the same thing, if x goes to infinity or x goes to minus infinity. So in other words, my polynomial function at infinity or minus infinity, it behaves like my leading term. Okay? So as x tends to infinity or x tends to minus infinity, a polynomial function functions and behavior is the same as its leading term. And the leading term is a power function, and we know the long-term behavior of power functions. Okay, so f of x is approximately minus 3x cubed when x goes to plus or minus infinity. So that means that as x tends to infinity, f of x is going to have the same behavior as minus 3x cubed. Now, okay, now x cubed looks like this. Minus 3x cubed, you have to flip the graph around like that. So that's the long-term behavior of my leading term. So I just need to look at what happens if x is large and negative. I'm going to have large negative values. So that's what's happening with my f as well. So x tends towards minus infinity. And as x goes to minus infinity, f of x now, x minus infinity, I'm going to have large positive values. And that's my long-term behavior for my polynomial. Finally, on an exam, let's say I write this down, I could always verify this by plugging in a large positive number first, but you don't have to be very large, like for, as soon as you got large, like x cubed, x5, they're going to become pretty big, even if x is not that big. So f of 100, okay, if you plug that into your initial polynomial, remember it was minus 3x cubed plus 2x squared plus 1, so you will replace x by 100. If you do that on a calculator, you're going to get minus 2,979,999. So as you can see, that's pretty large and negative, which is what we expected, right? You see it here. We expected large negative values. And if I look at f of minus 100, okay, so I'm not that large and negative, but anyway, we're going to see that we're going to get like a pretty big number, 3 million something, okay. Okay, so that verifies the second statement that I wrote here. Okay, so this is just a way of just checking with a calculator that what you wrote down makes sense.